Hello there, and welcome to this collection of notebooks and tutorials on advanced digital signal processing. This is a course offered by Professor Schuller at the UMNL University of Technology. I am Renato, and on this notebook we'll continue talking about filters, and then we'll see the multi-rate noble identities. So the idea is that we will go through some basics of filter design, and then we will see some examples in Python of filter design, and we also will see some filtering and sampling and upsampling and downsampling using the multi-rate noble identities. And let's get started. In general terms, we start designing our filters by specifying phase and magnitude. So this is how the frequency response of a filter looks like. So we have here our phase, that is independence of our normalized frequency capital omega, and here we have our magnitude. So when we design our filter, we need to specify both the phase and the magnitude. So let's talk about linear phase and signal delay. So the phase angle of our system is connected to the delay of our system. So if we have a pure delay of these samples, this will result in a transfer function in the z-transform domain like this, z to the power of minus d, where d is a delay of these samples, and we will get the frequency response in the discrete time Fourier transform domain, the dtft, if we replace z by e to the power of j capital omega, like this, and then our phase response looks like this. So we can see that there is minus capital omega times d. So the other way around, we can obtain the delay in samples if we divide the phase angle by the normalized frequency. So our delay is given by, this is the angle of our frequency response, and we divide by our normalized frequency, we get our delay. Yeah, it's important to observe that in Python, the function from numpy angle returns the angle of a complex number in radians, so between 0 and 2 pi, and this is suitable for our normalized frequencies. If the phase angle is a linear function in capital omega, if a slope of minus d, we call it a linear phase. So here we can see that there is the slope minus d, and there is a linear phase. Yeah? Observe that only in this case we have the same delay d for all frequencies. Yeah? We can also see that the negative slope of the phase curve corresponds to the delay d. So this linear phase is important, for instance, for image processing. So edges contain many different frequencies, and if we had different group delays for different frequencies, edges would dissolve and appear unsharp. So if the phase and delay is not important, often a linear phase is still chosen as a default for a filter design. We've seen the linear phase, and now we'll see a general phase and signal delay. So in general, we'll call the negative derivative with respect to capital omega the group delay, which may be dependent on the frequency capital omega. So if we call the group delay the d with the subscript g of capital omega, then it's defined as minus the derivative of the phase with respect to capital omega, and it is a very important definition. This means that the phase tells you how much delay each frequency group has through the system. When we design a system, this is what we need to keep it in mind. When we design a filter, we need to pay attention to both phase and magnitude. So now we also need to think about the desired magnitude, A of capital omega of our filter. So often one or multiple pass bands are desirable, where the signal is passed and hence has close to 0 dB attenuation, together with one or multiple stop bands at which frequencies the signal is stopped, meaning that it has strong attenuation. To do that, we need to decide where the band edges are in normalized frequency. So the filter coefficients of an FIR filter, the finite impulse response filter, are its impulse response. So we can obtain the ideal impulse response of a desired filter design in the frequency domain by applying the inverse dt of t to it. The thing is that an ideal filter in general is infinitely long. It goes into the past and in the future, and it's not realizable. So what we can do is that we can approximate our desired frequency response by minimizing, for example, some error functions that which we need to define according to our application requirements. Yeah? Since we have no ideal filters, first we need to give the system some transition bands between the pass bands and the stop bands to give the filter space to come from one state, the passing state, to another state, the stopping state. So this means there need to be gaps between the pass band and the stop bands. Let's take a look into this example now. We would like to have a half band low pass filter. So this means that we would like to have a pass band from frequency 0 up to the frequency pi divided by 2. So this is a half band filter. If we want to use it for sampling rate conversion with a downsampling factor of 2, we actually need to make sure that the stop band starts at pi divided by 2. We also need to create a transition band, for instance, from going from pi divided by 2 minus 0.1 to pi divided by 2. So this transition band is where we don't care about the value of our frequency response, and it's something that we can use to fine-tune the resulting filter. So for instance, if we see we don't get enough attenuation, we can increase the bandwidth of our transition band. Here our pass band is given as between 0 and pi divided by 2 minus 0.1. So we having this transition band, yeah, and we have our pass band from 0 to pi divided by 2 minus 0.1. This is still not an ideal filter. Yeah? So we can also define an error measure or an error function which measures how close we come to the ideal, so how good the filter is, which we can use to obtain a design minimizing this error function. So the often used error functions are the mean squared error, the mean absolute error, the weighted mean squared error, or the minimax error function. So this minimax error function seeks to minimize the maximum deviation to the ideal. So the weighted mean squared error uses weights to give errors in different frequency regions with different importance. So for instance, the error in the stop band is often more important than in the pass band to obtain a high attenuation in the stop band. So an error of 0.1 in the pass band might not be so bad, but an error of 0.1 in the stop band leads to perhaps only minus 20 dB attenuation, which is not very much. We optimize in the linear domain and not in the dB domain. So in this case, we might assign a weight of 1 to the pass bands and a weight of 1000 to the stop bands to obtain higher stop band attenuations. So the optimization usually results in the same or similar weighted error for all frequencies. So for FIR linear phase filters, Python has a specialized optimization in the function remes. So it's from the SciPy signal libraries, which implements the so-called Parkes-McClellan algorithm using the Chebyshev algorithm. So you can also take a look at the discrete time signal processing book from Oppenheim, and you can see some description about this algorithm. So now we can have a little example using this minimax error function. So the algorithm minimizes the maximum error in the pass band and the stop band, weighted in comparison between the two, which leads to a so-called equiripple behavior. So all ripples have the same height in the same band, so in the stop band or the pass band of the filter in the frequency domain. So we can take a look at the remes function for the SciPy signal. So we can see here, this is the help. So this is how the function looks like and all the possible arguments. So this function calculates the minimax optimal filter using the Remez exchange algorithm. So it calculates the filter coefficients for the finite impulse response filter, whose transfer function minimizes the maximum error between the desired gain and the realized gain in the specified frequency bands using the Remez exchange algorithm. So it has the parameters. So num taps is the desired number of taps in the filter. So this is the filter order +1. The bands, so it's a monotonic sequence containing the band edges, so all elements must be non-negative and less than half the sampling frequency as given by Fs. So this is the desired argument. So this is the sequence, half the size of bands containing the desired gain in each of the specified bands. Then we have the weight, so it's a relative weighting to give to each band region. So the length of weight has to be half the length of the bands. Then there are some other parameters. So we can set which kind of filter. If your type of filter is a band pass, so it's a flat response in bands. This is the default. It can be a differentiator, so the frequency proportional response in bands, or Hilbert, this filter with odd symmetry, so it's a type 3 or type 4. For odd order, type 3 for even orders. So you can take a look how to use some examples here, and we will use this function in our example. Here's our Python example. We're defining the backend for the matplotlib as notebook, so it will be some interactive pictures like this. Then we're importing matplotlib pyplot as PLT and importing SciPy signal as SP. Here we are defining the length of our filter, so there will be 8 number of taps equals to 8. Here we are defining the vectors, then the amplitude, and giving the weights. So we are giving a weight 1 and weight 100. Here we are having the impulse response by calling the Remez function with these parameters, and here we are plotting the impulse response of the filter. So we have 8 samples, the impulse response, and this is the value. So we can obtain a nice impulse response or set of coefficients, and then we can see what's the frequency response of this impulse response. So now we are importing the frac_z function from the SciPy signal. We're importing numpy as np. This is just a nice trick in matplotlib, so that I want that the values here are in functions of pi. So when we plot something like this, it will be here 3.14, so it will be 0 and some numbers. But when we use this function formatter and multiple locator, we can set this axis as multiple of pi. So here we are using calling the frac_z, and this is the impulse response that we got from the Remez algorithm. So these are the frequencies which the frequency response was calculated. Now we're defining a figure, a plot. So this is what we're doing here, and we are plotting the 20 log of the magnitude of the calculated frequency response. And these are the frequencies. Here we are using this set major formatter, so this is what we're doing to convert the numbers into multiples of pi. Here we are plotting the phase, so we are using the unwrapped version of the phase, and here we have the frequency response of our filter that we calculated using the Remez. So we can see that there is an attenuation here. Here's the pass band, and then we have the stop band, and here is the frequency. Here is our normalized frequency from 0 to pi, which is the Nyquist frequency. So here we see that we obtain about minus 40 dB in the stop band. So it roughly corresponds to a weight of 100 for the stop band. Here's another example. This time we will listen to something, so we will have an example with sound. And in this example we have a sampling rate of 8 kilohertz, and we want to build a bandpass filter. So for this filter, our low stop band will be between 0 and 0.0.5, our pass band between 0.1 and 0.2, and our high stop band will be between 0.3 and 0.5. So here again we have 0.5 as the Nyquist frequency and 1 as the sampling frequency. So our pass band will be in between 0.1 times 8 kilohertz, so 800 hertz, and 0.2 times 8,000 hertz, which is 1.6 kilohertz. So here we are defining our factor for bands. So there's 0 and 0.05, 0.1 and 0.2, 0.3 and 0.5. So we're defining our low stop band, our pass band, and our high stop band. So this we can also have the desired magnitude per band, and here we have, for example, 0, 1 and 0. So 0 for the low stop band, 1 for the pass band, and 0 for the high stop band. And we choose our weights. So here we're choosing 100 for the low stop band, 1 for the pass band, and 100 for the high stop band. And in this case the number of taps n equals to 32, so this is the filter length. So again we're defining here our filter. So we are using the Remes algorithm, using the SciPy signal Remes function. So we're importing NumPy, SciPy signal, matplotlib. This we are defining the length of our filter, the number of taps. Here we are defining our filter. So this is the bandpass filters. So we are passing all the parameters that are necessary, and here we are plotting the frequency response using the FracZ function from SciPy signal like we did previously, and this is the magnitude of the frequency response of our bandpass filters. So here, as you can see, I didn't use that matplotlib trick, so it's giving me from 0 to 3.14, so this is pi. And we could also apply the same thing what we did before and have here multiples of pi if we would like to do that. So again, here it is the normalized frequency, where pi is the Nyquist frequency. So observe that the equiripple behavior inside each band. We see our pass band a little to the left of the center. The side lobe to its right is from the transition band there. So this is our pass band, and we have low stop band, high stop band, and we can also plot the impulse response. So this was just the B pass here is the impulse response. So when we plot here, this is the impulse response of our bandpass here, and we can see that the impulse response is symmetric around the center because it's a linear phase filter, and it still has a similarity with a sinc function. So first we designed our filter, our bandpass filter, and now we'll move on to use this filter in this example, where we use Pi audio to get the audio from a microphone. So here I'm importing NumPy, I'm importing Pi audio, and some functions we're going to use, and some constants. I'm importing IPy widgets so we can use some buttons. I'm importing the threading and SciPy signal. So this is for the filter. The threading is we're running things on separate threads, so there's not blocking. We can have access to the GUI with buttons. So here I'm defining a function to turn filter on and off. We're defining some buttons to stop. So when I run the cell, it will automatically start capturing audio from the microphone, and when I press stop, it will stop, and it will do all the closing procedures for Pi Audio. We also have a checkbox to turn the filter on and off. So here is the function that when we press the stop button, all of the things will happen here. We will stop the stream, we will close the stream, we will terminate Pi Audio, we'll make the button disabled, and we'll print Pi Audio terminated. So here, when we click the checkbox to turn the filter on and off, we will just turn the filter variable to true or to false. Here we are displaying the boxes. So here is we are defining our filter exactly like we did here. So we're doing this here now, and here this is our callback for the Pi Audio. So we are running Pi Audio now using the callback mode. So when there are enough samples, then Pi Audio will run this callback, and we'll get audio data from the buffer. And if the filter is on, then we will filter the signal, and if the stop button is pressed, then we will stop everything. If the filter is off, then we'll just pass data as it is. Here we are defining our stream for Pi Audio. We are using 8 kilohertz, it's mono, so we want to get the audio from the input, and we want to listen to the audio, so we are also setting output true. We are using 1024 frames per buffer, and here is the callback that we define here, the stream callback. We need to pass it here, and Pi Audio recommends this keep alive, so to have a sleep, so while the stream is active. And now I'm creating a different thread to run this keep alive, and then we're starting the stream, and then we're starting the thread. So we can take a look. Teste som. So now the filter is off. So we see that this it sounds a bit like a cheap telephone. So we have a very small band to our audio when the filter is on. So usually a telephone bandwidth is about 0.3 to 3.4 kilohertz, and this was this example using Pi Audio and a filter using the Remes algorithm. We've seen some more on the basics of filter design, and now we'll move on to filtering and sampling, specifically the multirate noble identities. So here we see filtering including downsampling. So there's convolution including downsampling. We have our input signal, and we have here the convolution. So there's filtering, and we have a downsampling and filtering. So this is the convolution with downsampling formula right here. This is an implementation of our input signal. We filter and we downsample, and we have our result. For multirate systems, the so-called noble identities play a very important role. So here we have the noble identities. We have this section here for downsampling, and this section here for upsampling. And here we see that on the left side we have our signal, then we first have the downsampling, and then we have the filtering. But on the right side we have an equivalent to this operation, but first we filter using a different filter, not this one. This is a upsampled version of this filter, and here we do the downsample after filtering. So these are the noble identities for upsample and downsample, and the equivalent that we first downsample or upsample and then we filter, or we first filter and then we downsample or upsample. So the symbol with this arrow pointing down means the downsampling by a factor of n, and we achieve this by keeping only every nth sample. And the symbol with the arrow pointing up means that we're upsampling the sequence by inserting n minus 1 zeros after each sample. So we can have an example if we have a filter impulse response given by this array here. So we have 1, 2, and 3. And then if we take the z transform of this impulse response, we will have 1 z to the power of 0 plus 2 z to the power of minus 1 plus 3 times z to the power of minus 2. And for n equals to 2, we have an upsample version that is given by this here, which corresponds to the upsample. So it is sparse because of the zeros in it, and the impulse response then will be 1, 0, 2, 0, and 3. So we're inserting zeros, n minus 1 zeros after each sample. So the noble identity will tell us in which cases we can exchange down or upsampling with filtering. This can be done in the case of sparse impulse response, as can be seen above. So observe that this frequency response h z to the power of n, that is the upsampled version of h of z. So remember that the upsampled impulse response has n minus 1 zeros inserted after each sample of the original impulse response. As we can see here, this is the original impulse response, and this is the upsampled version. Yeah? So in Python, we have here, we are defining this array of numbers. This we are defining the sampling, the upsample or the downsample factor. That's n equals to 2, and here is our array. So what we want to do now is that we want to implement the first block diagram of the noble identities, the downsampling. So this is the pair on the first line with inputs y1 and y2. So this is the pair that we want to implement. First, for y1, this is first downsampling and then filtering. So the downsampling by a factor of n equals to 2, we can use this Python indexing. So we are keeping just every nth sample. So this was our original. Then we'll have 1, 3, 5, 7, and 9. Then we'll apply a filter. We're using the L filter from SciPy, and this will yield to the sum of each pair in x of d, and we will have y1. This will be what we have here. So now first filtering and then downsampling to implement the corresponding right hand side block diagram of the noble identity. So this part here, first filtering and then downsampling. So what we have, we will have here an array with zeros. Then we will include some samples. Then it will yield to this here, because we had b equals to this. When we do this operation here, we are inserting a 0 here. We also can use the SciPy filter, and we will have this, and then we will get the y of u, which is here, and then we downsample, and we will have the y2, and we see that they're both y1 and y2 are identical. Yeah. So let's do this using Python. We had our original array here. So now we are doing this x of d. So this is the downsampled of x. So this is our b. This is the filter we are going to use. So y1 is the x of t. We apply this filter b, and we have y1, which is this part here. And now we are doing this operation here. So we had what we explained here, and then yu, we are having our original signal x, and then we are filtering with this b of u, and then we have y2, and then we apply the downsampled version of this, and this is what we have here, and we see that y1 is equal to y2. So this is, we're implementing these parts here when we're showing that is the same if we do y1 is equal to y2. The difference here is that first here we downsample and then we filtered, but here we first filter by a upsampled version of the filter, and then we downsample. So this is what it's implemented here. We have this upsampled version of the filter, and we filter and then we downsample, and we see that this they're both the same. So these noble identities can be used to create efficient systems for sampling rate conversions. So in this way we can have filters which always run on the lower sampling rate, and that makes the implementation easier. Now let's remember that so far we've just did the filtering at the higher sampling rate. So it's also possible to rewrite a filter as a sum of upsampled version of its phase shift and downsampled impulse response, as can be seen in the following decomposition of a filter h of z. So in this way we can make out of our previous useless filter, so we will make it a useful filter when we combine several of our upsampled versions into a new usable filter. So what we will do is something what is called a kind of a polyphase decomposition. So we will have polyphase components or polyphase elements. So this is what we're doing now. We are rewriting a filter as a sum of upsampled version of its phase shifted and downsampled impulse response. So we see we have there is phase 0, phase 1, and so on. So here this H0 contains the coefficients of our original filter at positions at m times capital N. So this is phase 0. Then this H1 contains the coefficients at position m times capital N plus 1. So this is the phase 1. And in general we will have the H of I, z to the power of n, which will contain the coefficients at position m times capital N plus 1 at phase I, plus I at phase I. So this means that the H of I of z is the z transform of the impulse response of m times capital N plus y, I. So this is H of n is the impulse response of our original filter. So this is some kind of a polyphase decomposition that we are rewriting a filter as a sum of upsampled versions of its phase shifted and downsampled impulse response. So it can be seen that there are many phases of our impulse response. So the components, each one of these components are called polyphase components. So this is just to illustrate, as an illustration, we see a simple time sequence, and then the sequence for a sampling factor of n equals to 3 that will be decomposed into 3 upsampled polyphase components. So first we're taking 1, 4, 7, 1, 4, 7, and we have zeros in between. Then we have 2, 5, and 8, and we also have these 2 zeros. Or we can have also is 3, 6, that is shown here. So the upper plot, so this is the phase 0, the middle is phase 1, and this is phase 2. So the same can be done for our signal x of n. So our polyphase component h of I is the z transform of x m times capital N plus I. Here we have an example. So the impulse response of our filter is given by this vector here. So it's 1, 2, 3, 4, and so on. Then its z transform is 1. So this is the z to the power of 0. Then we have 2. This is z to the power of minus 1. 3 times z to the power of minus 2. 4 times z to the power minus 3, and so on. So when we assume a sampling factor n equals to 2, we can obtain its upsampled polyphase components given by this. So here is phase 0, and here phase 1, for example. So we have 1, 3, 5, and so on. And with phase 1 is 2, 4, 6, and so on. And we can combine these two, giving exactly this. So if we add the phase 0 component with phase 1 component, we will end up, and all the components, we will end up with the frequency response, the Z transform. So the general case is illustrated in the following block diagram that consists of a delay chain on the left to implement the different delays, Z to the power of minus I, and the polyphase components. So here we have the polyphase components, here we have our delays, here we have our input, this is the filter output, this is downsampling, and here we have our output. So this could be a system for downsampling rate conversion, where we first low pass filter the signal X to avoid aliasing, and then we downsample it. So in this way we can decompose our filter in n polyphase components, where I is the phase index, like we showed before, and we can simplify the system using the noble identities. Because in the sum we have the transfer functions of the form of h of I z to the power of n, we can use the noble identities to simplify our sampling rate conversion, to shift down samplers before the sum and before the filters, but not before the delay chain on the left side, and replacing the polyphase filter arguments z to the power of n with z. So now we have our input x of z, then we have here our delays, here we have the downsampling, here we have our filters, and then we have our output. So we are moving the downsample. Here we have our polyphase components, and we have our output. So looking at the delay chain and the following downsamplers, we see that this corresponds to blocking the signal X into consecutive blocks of size n. So this can be seen as a serial to parallel conversion for each n samples. So now we have a blockwise processing with our filter, and the filtering is now completely done at the lower sampling rate. That will reduce the speed requirements for hardware. We obtain the parallel processing at a lower sampling rate. Since we have n polyphase components in parallel, we can also represent them as polyphase vectors and obtain a vector multiplication for the filtering at the lower sampling rate. So is what we have here is if we have more than one filter, also we can collect the polyphase vectors into polyphase matrices. Observe that this is a very convenient description because it includes sampling as part of this simple vector multiplication. So here's a Python example, downsample. So we will downsample an audio signal. In this case is the great rock song Long Way to Go from the band called the Identities. And what we're doing is we are using a librosa to load this mp3 file into this variable x, and then we're playing using IPython display, and we're playing just 10 seconds of the song shifted at 10 seconds from the beginning. So this is how the song sounds. So we will take a low pass filter with the impulse response given by this right here, and we will use a downsampling factor of n equals to 2. So we have here, this is our impulse response. If we take the Z transform, we will have this here. So this is the coefficients. So Z to the power -1, -2, -3. And then we can have the polyphase components starting at phase 0. So we have these two coefficients, and for phase 1 we have these two coefficients. So we can use this Python indexing to conveniently have this polyphase components. So from here we go to H0 and H1, and we can do the same thing. So we will have the downsampled input signal X. So we had our original signal here, and we'll just use this indexing to get the X0 and X1. So then if we remember that the multiplication in the Z domain is a convolution in the time domain, so then the filtered and downsampled output will be given by this. We can use the SciPy signal L filter. So here we are filtering X0 with H0 plus filtering X1 with H1. So let's do this. We have our impulse response here. We're defining it here. Here we are having our polyphase components for the impulse response. Here we had our X signal, and now we are having downsampled versions of the original signal, phase 0 and phase 1, and here we are filtering and adding. So observe that each of these two filters now works on a downsampled signal, but the result is identical to first filtering and then downsampling, and we can listen to the result. So we see that the sampling rate now is half of what it used to be, and we also have this filtering. So corresponding upsamplers can also be obtained with filters operating on the lower sampling rate. So we are making use of our noble identities to have filters operating on the lower sampling rate. So we have this, they are linear time invariant, and we can exchange their ordering. So we are redrawing the polyphase decomposition for an upsample, followed by a filter at the high sampling rate as follows. So here we have the delay elements shifted to the output. So we are shifting the delay elements to the output. So we have upsampling followed by a low pass filter just here. So using the noble identities, we can now shift the upsampler to the right behind the polyphase filters with changing their arguments from Z to the power of capital N to Z, and before the delay chain. So we have polyphase components given by this diagram here. So this is a picture 2. So again, this leads to a parallel processing with n filters working in parallel at the lower sampling rate. We have n filters in parallel at the lower sampling rate. So the structure on the right with the upsampler and the delay chain can be seen as a deblocking operation. So each time the upsampler let a complete block through, it is given to the delay chain. So in the next time steps, the upsampler is stopping letting through, and the block is shifted through the delay chain as a sequence of samples. So this can also be seen as a parallel to serial conversion. So with the polyphase elements y of I of z, the processing at the lower sampling rate can also be written in terms of the polyphase vectors. So observe that if we have more than one filter, we can collect the polyphase vectors into polyphase matrices.